So it turns out that when you're looking at a chemical reaction, almost all the energy is involved in making and breaking the bond. So if you keep track of all the different bond strengths, you can actually calculate heats of reaction from that, with a small amount of error. Because the enthalpy of reaction, well, it's mostly has to do with the bonds making and breaking, right? So that's what we're dealing with. So if we have all of these bond dissociations tabulated, we can estimate the heat of reaction by simply looking at the sum of the energy formed when we break all the bonds and subtract out the energy of the bonds formed. So bonds broken minus bonds formed. This is a little different than heat of reactions from heats of formation, right? There it's the heats of formation of the products minus the final products minus the reactants. In this case, it's bonds broken minus bonds formed. So it just you have to keep track of all the minus signs to make sure that you're doing it right. So you break all the bonds and you get all that, you have to get all that energy, and then you subtract out the energy that comes together when the bonds are formed. Okay, so let's actually try and put this together. So if we're dealing with H2 gas plus F2 gas to produce 2 molecules of hydrogen fluoride, then if we have a mole of that, we're breaking a mole of HH bonds, we're breaking, and also a mole of FF bonds, and we're gaining 2 moles of HH bonds. So we can write this out. And so we've got the bonds broken. Well, we've got an HH bond, so we've got 436 plus an FF bond that isn't quite as strong, 159. And then we subtract the bonds formed. We have 2 times an HF bond is 570. That's quite a strong bond. And so if we add those all together, we get minus 545 kilojoules per mole. And that is an exothermic process. We're going downhill in energy. It's much more stable to have HF than to have individual hydrogen and fluorine. And so therefore, its exothermic process energy is given off into the environment in that case. Now you notice this is actually like twice the energy of the heat of formation, right? The heat of formation of hydrogen fluoride would be half a mole of H2 plus half a mole of F2 is equal to 1 mole of HF. So if we divide this by 2, we get minus 545 divided by 2 equals minus 272.5 kilojoules per mole. And if we look up the heat of formation, so this is approximately the heat of formation of hydrogen fluoride. If you actually look it up, it's actually the real delta HF is minus 273.3. So really close, within a kilojoule per mole, because the energy in these bonds, which is relatively consistent across molecules, but it's not exactly consistent. That's why these are not down to the decimal places. Then these energies are essentially they're quite good. They're quite good approximations to the heats of reaction.